Thank you for coming to this last lecture. Today, I'll mainly bring it back to talking about free-by-cyclic groups, but I want to sort of wrap up the things I wanted to say with automorphisms of free groups. So at the end of the lecture on Tuesday, I stated this equivalence, this application of the theory of relative train tracks to characterize being polynomially growing. And one of its corollaries is that an automorphism is either polynomially growing or exponentially growing, because the way I defined these two things, it was not clear that, those were the only options you can get with an automorphisms. And in a moment, I'll give examples of relative train tracks and how I personally think about them. And then we'll move on to talking about free-by-cyclic groups. I wanted to add some other conclusions you can make from this equivalence. So one corollary that's also not obvious is that if phi is polynomially growing, so is the inverse. And this here was polynomially growing was only defined by looking at lengths of conjugacy classes under forward iterations. So there's no reason why you should immediately believe that backward iteration also gives you the same growth type. With this characterization one, you can sort of show that if you have a relative train track where all the stretch factors in each strata are one, then the inverse has the same different map because it's the inverse, but on the same graph and same filtration, you get a relative train track for the inverse with the same properties. Oh, so I had that as an exercise, but I think that's kind of mean. It's yes, they have the same degree, but it's this is not strong enough to prove that. So you might want to talk about stronger properties of relative train tracks. Yeah, and that maybe leads into the quotation marks here. What I've defined here is not really the definition of a relative train track you'll see in Besvina Handel's paper, but it is sort of like the most basic form I can give that still allows you to prove some things, but things like computing the actual degree, it's not strong enough to just see it. What else did I want to say about this? All right, so facts, I guess I'll say. And another corollary was that the degree of the, I defined the degree of the whole automorphism, then that's finite. So there's a uniform bound on the degrees for each element as you look at its growth. And that is essentially n is an upper bound. And n here for me, some other disclaimers that I probably didn't mention before. People usually talk about Fn where the subscript is the rank. I never did that. So I want to keep subscripts for indexing filtrations. So n here is the length of the filtration.
Is there a relationship between this n and the rate? Is there a relationship between this n and the rate?
Yeah, there's something like n is less than or equal to, I don't know, twice the rank. Is one crude upper bound you can put there. So I had, so the degrees, so they're both polynomially growing. The degrees should be the same. So I'm not going to write that as a fact. And so only one fact here. The last thing I want to say is that being polynomially growing is equivalent. Same thing, or no. Being has finite order is the same as being polynomially growing with degree equal to 0. And again, that's not entirely obvious. What does it mean to be degree 0? It means the growth of a conjugacy class is bounded by a uniform constant. There are only finitely many conjugacy classes with a bounded constant, so that's actually telling you every conjugacy class is periodic. And this here is now saying if every conjugacy class is periodic, then some power of your automorphism is an inner automorphism. You can take that as an exercise. You don't really need relative train tracks to prove that. You can sort of pick a basis and then pass to a power where each basis is sent to its conjugate and then show that an automorphism that does that has to be an inner automorphism. So some examples. We had, I'm going to give you an example of a relative train track. So the automorphism I'm interested in is A goes to B, B goes to C, and C goes to C, A, B inverse. And another automorphism over here, the free group on X and Y. So I'll call this phi, and this is going to be psi. X gets mapped to Y, and Y gets mapped to X. And this is psi. All right, so when I talk about relative train tracks, you want to maybe start with the rows where the marking is each petal corresponds to each of the spaces. So you have a petal for A, a petal for B, and a petal for C. And then you do the obvious map that sends the edge A to the path B, B to C, and C to the path C, A, B inverse. But that's going to be a topological representative. It's going to be irreducible, but it's not going to be a train track because once you start iterating, you're going to see cancellation happening somewhere in the image of C after a while. So if I wanted a relative train track, it turns out over here, I'm going to write C prime. I'm going to choose a new basis. And C prime is going to be C A. And CA is fixed. And over here I have B and I have A. So this is still a basis for of my free group. It just looks slightly different. And then the automorphism is going to look like C prime gets sent to C prime. B gets sent to C, what? C prime A inverse, thank you. So I get that. So now I can sort of do the obvious map in this marking. So it's a different, it's still a rows, but now one petal corresponds to CA rather than C. And so now there I'm going to get a filtration with C prime is invariant loop. And then I have A and B. And now how do I think of this relative train track? I'll have gamma 1, which is the top graph. And then I have gamma 2. My filtration is going to have length 2, n equals 2. And at the bottom, I have a circle, which has been labeled C prime, or I'm just going to go back to writing ABC here, CA. And then, since I'm thinking relatively, I'm going to write the free splitting instead of writing the whole graph. So over here, I'm going to have a graph with a petal for A and a petal for B. And then the vertex here, I'm going to remember that there was some invariant subgraph, but I'm not going to write it down. I'm going to instead mark that vertex with the subgroup corresponding to that subgraph. So the subgroup here is the subgroup the vertex group is going to be the cyclic subgroup free factor generated by CA. Yeah. So now this is it's a graph of groups decomposition of your free group where you have a cyclic vertex group and your edge stabilizers are trivial. It's known as a free splitting. And the reason I like this is because now, if you think about what the map, like what this map is doing to this graph, over here, well, this was invariant, so I can restrict the map onto that pedal and it's just fixed. All right, and that's where it, so now over here, I have the restriction G2, which was the restriction of G to gamma 2. And that's just going to be the identity map here. And then over here, I'm going to have G, since I've collapsed something, I now have G hat 1. That's what my notation for G hat was. It's sort of like the induced map on the free splitting. And over here, what it's doing is it's acting on the vertex group by identity or some automorphism. You kind of don't care what the automorphism is. But then it's flipping, it's sending A to B and B to A inverse. As far as this automorphism is concerned, this thing is not there. Like, as far as the free splitting is concerned, this is not there, no way. Okay, in the orbits are being permuted. So in the Bassler tree, the orbits are being permuted, yeah. So A gets sent to B and B gets sent to A. So over here, I'm going to see, like in the Bassler tree, I'm going to see a simplicial automorphism. And having a simplicial automorphism is exactly the fact that lambda 1 is going to equal 1 here. And this being the identity also tells me that lambda 2 is 1. And I did bring up this example for a reason. I guess, and I didn't have lots of examples, but you should always, you might have been curious about how a free bicyclic group can be written as a free bicyclic group in different ways. So the mapping torus of this and the free bicyclic group for this are actually the same. So G phi over here has the presentation A, B, C, and T. And I'm going to conjugate T, A, T inverse to B, dot, 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 T, C, T inverse to C, A, B inverse. And then I'm going to do some transformations to this presentation. This presentation tells me I don't really need B because B is TA inverse. So I can get rid of B. And then the second the second relation will have told me I don't really need C because I can rewrite it in terms of A and T as well. So I can get rid of this 2 and just be left with A and T. And now this last relation becomes T cubed or T squared. T cubed A T to the inverse equals, this is T squared A T to the multiplied by A, and then B is T A inverse T inverse. So I now have a two generator, one relator group, and I can set Y equal to AT inverse, and this becomes T Y T inverse equals Y T inverse Y T Y inverse. What else do I want to change here? Set X equal to T inverse YT, and S equal to Y inverse T, and you're going to get the presentation for the free bicyclic group of this with sort of S as your stable letter instead. So I'm not going to write out all the details, but this is going to be your isomorphism. Typically, the only way I know how to come up with cook up examples is through one-related groups. Unfortunately, that will be a whole different course to discuss. All right, so here's an example of two different automorphisms, different ranks. But now we know this is finite order. So if being finite order is a group invariant, we should expect this to be finite order. And it turns out to be true. Phi to the 4 is an inner automorphism. All right, so can you move this?
JP, how would you just check that, like, this is degree 0?
What?
We know it's polynomial growing, so you check the lambda i's are 1. How like easy or hard to just check directly that it's degree 0?
Well, no, you can just check that it's finite order.
It's easier to check finite.
Yeah. Well, I don't know. I knew it was going to be finite order, so I can just keep on doing it, but that would be an infinite check if it wasn't. So maybe what you want to ask is, how do you check if something is linearly growing? Yeah, we don't have the tools listed over here. It's a good question, but I now want to move on to the next. So free-by-cyclic groups. So a group has a cyclic splitting. That a group G has a cyclic splitting if you have an action of G on a simplicial tree. Let's call it a tree T if we want a name. And I want this action to be minimal. Well, it's a simplicial action, it's minimal. That means there is no invariant proper subtree. And then I want it to have without inversions. So if it fixes a point in an edge, it fixes the whole edge pointwise. It doesn't sort of like flip an edge onto itself. And then this is just a splitting. If you only have 1 and 2, that's basically what a splitting is. And a cyclic splitting then means you're putting restriction on edge stabilizers. So you have cyclic edge stabilizers. And I've already discussed free splittings. Free splittings are when you have an action like this, but your edge stabilizers are trivial. Edge stabilizers are trivial. Okay, we say phi, an automorphism phi has fixes a free splitting. Fixes a free splitting if F acts on T is a free splitting, or minimal without inversions and trivial edge stabilizers, and there exists a phi equivariant simplicial automorphism alpha from T to T. So what does being phi equivariant mean? It means if you pick a point P in your tree and you act on it by an element of your free group and apply the automorphism, then that's the same as applying the automorphism to just the point and then acting on that by the image of A under your automorphism. Okay, so we've seen fixed free splittings. This is an example of a fixed free splitting. This is another example of a fixed free splitting. And the point here is that if you have a fixed free splitting, then you can extend this to an action of G phi of the free-by-cyclic group onto the same tree T. So having a fixed free splitting implies that G of phi, I get an action of G on phi on the same tree T is a cyclic splitting. Yeah. So what is this action? Well, we know how elements of F act. Like I have to be once again kind of careful here. This here is the semi-direct product of phi F and Z. So we know how F acts. I just need to tell you how T acts, how the generator of the integers acts. So, and I want T to act on a point P by that automorphism that is phi equivariant. And this equivariant relation is exactly the relation you want to check that this is an action of the semi-direct product. So in orange, I'll sort of write, what's the thing you want to check here now is that if you have TA acting on a point P, then if it's actually an action of the semi-direct product, then the relation is TA is the same as phi T, right? TA is equal to this was my relation on how I define my free-by-cyclic group. And then I want this to equal that, and it pops out just from this condition over here. So whenever you have a cyclic splitting, a fixed free splitting of an automorphism, then you get a cyclic splitting of your free-by-cyclic group. And it goes the other way as well. So there's a proposition. It's first stated in a Kapovich-Kleiner paper. In 2000, they're interested in atoroidal cases. And then there's Brinkman was interested in more general setting. This was later. So if you want a reference to see where this proposition is proven, there are two proofs. There is basically the same proof. Cyclic splittings of G phi are in one-to-one correspondence with fixed phi fixed free splittings. I guess. Thank you. So if I fix one presentation of G phi, then I can sort of go back and forth between fixed free splittings. But then, of course, if this happens to be isomorphic to G psi, then now I'm getting a correspondence between fixed free splittings of psi with fixed free splittings of F. So this here just describes how to move from this to this. And the content of this proposition is going, if I have a cyclic splitting, how do you get a free splitting of F? And essentially, you just restrict the action of G on your tree T to the action of F on the tree T, and you use the fact that F is normal and some, I don't know, like Basser theory or some conditions to prove that that action is going to be co-compact and have trivial edge stabilizers is the thing you want to show. All right, so corollary now is that I told you that being polynomially growing is the same as having a relative train track where all the stretch factors are 1. And in the language of free splitting, that means I have a fixed free splitting. And if I restrict to the vertex group, that has a fixed free splitting. And if I restrict to the vertex group, that has a fixed free splitting. So P is polynomially growing if and only if G phi has cyclic splitting. Maybe I'll just write Z splitting from now on. With vertex groups, vertex groups G2. So now maybe it's not just one orbit of vertices, but you might have several orbits, who cares? And then G2 has Z splitting with vertex groups script G3 all the way down to Gn is, so at the bottom you should have something where you just have the identity, and that gives you, or at the bottom you should have something that's finite order, so that gives you, is virtually a product. So this proposition, having equivalence between fixed free splittings and cyclic splittings, allows me to translate that exercise into a statement about the free-by-cyclic groups. And this is a purely algebraic statement, so it's a group invariant. And now I've proven that being polynomially growing is a group invariant. Corollary to the corollary is that polynomial growth is a group invariant. You can also show that it's a commensurability invariant, and there what you want to say is that having a cyclic splitting is invariant under passing to finite finite index subgroups or supergroups.
Yeah, because the length of this process is like the polynomial growth rate.
No, because of this example over here, the length is not. But that's yes.
So the degree of the polynomial, that's also.
It will be a group invariant, but it's not going to be the n here. But to answer your question, okay. So I'm going to just talk about JSJ decomposition, because then you sort of want to say having a cyclic splitting, like you can have lots of them, and now you want to have one with the smallest vertex groups. And if you have such a thing, then you can still sort of like now say, take a maximal cyclic splitting on each step, and the length of that, I think, someone should go out and prove it. It should be a good result. That length is actually the degree. Yes, I might get to that today. Well, I can say yes, but it's a deep theorem that having cyclic splittings is a QI invariant. So that's one way to prove it. Another way is to prove that it's not relatively hyperbolic, and that's also a QI invariant.
The length of this, the thing is the length of filtration.
Yes, the length here is going to be the length of your filtration for your. But as you can see, you can generally have different lengths of filtrations. Like this here was already a train track, right? But I could have also filtered it this way. I could get a barbell as my graph gamma 1, where gamma 2 is, this is X and this is Y, where gamma 2 is these two things and they're being swapped. So now I have a relative train track with this is a different fixed free splitting for the same group. Right, so just the decomposition. For the sake of time, I'm now going to state the full theorem. Rips, Sella in 97. JSJ really comes from study of three manifolds, decomposing three manifolds. But there's lots of people who sort of have extended it to a group theoretic setting. But in this specific case, I want to say, if you assume G phi has a cyclic splitting, then you can conclude that there exists some subgroup system, and it's unique, that is minimal that is the minimal vertex group system for some amongst all cyclic splittings. So you can look at the set of vertex, you go over all cyclic splittings of your group, and you look at all the vertex group systems you get. And those are partially ordered by containment. There's a minimal one, and the minimal one is unique. And here I'm being a bit finicky where you can either think of this as being just all this, like everything it's a union of subgroups, but that's going to be infinite, or you maybe want to think about conjugates, like a set of conjugates, and that's going to be finite if you think of it as a set of conjugates. There's more, there's a JSJ tree. It's sort of unique up to deformation, but I don't want to get into that. But the most important thing is that there's a unique thing you can define that's sort of like a smallest vertex group system for cyclic splitting. And here's a question that I'm curious about. If you started with phi being polynomially growing, and then you consider the script G to be the minimal. So we know, because it's polynomially growing, we know that it has a fixed free splitting, like the top strata of your relative train track. So now you take a minimal vertex group system of a Z splitting. So this is a well-defined thing. It's unique of G phi. And when you do this, then you can now intersect. You now have you choose some cyclic splitting that has G as its vertex group system, and then restrict to the action of F. That gives you a free splitting, and ask. That free splitting has some free factor system up to quotation marks. I'm looking at script G intersected with my free group F. So that gives me a free factor system down for the free group. This is going to be phi invariant because the free splitting is phi fixed. And my question is the degree, when you restrict to this free factor system, is this the degree of phi minus 1? If the answer is yes, then you can now use this maximal splittings to define also the degree as being a group invariant. I don't know. Seems like it should be true, but what?
The divergence of these groups, like, is it invariant and recover to the degree of polynomial group? Because maybe
yeah, but divergence just seems like if you just wanted to prove there was a group invariant, that's like a sledgehammer. I'm not there yet. I'm still talking about group invariance at the moment. All right, so now.
What would you rate of line respect to that?
So just for the sake of simplicity, assume G is a single group. It's not a system, it's not a union of groups, but just a single group. Then phi restricted to F is an automorphism of some free factor. So I'm asking about the degree of that automorphism on the smaller free factor. I just erased the example over here, but like we had G2 over here. And it's
And you have to sum them if there are multiple.
no, if they're multiple, you sort of want to take the maximum amongst each one. Or if you're like me and you're very happy just talking about group systems, and your groups don't have to be connected. So you can define everything. Everything I did here was graph gamma was connected, right? You don't need gamma to be connected to make any of the arguments work. So that sort of like saves you the worry of how to deal with the defining this other. Not everyone is a fan, so let's see. Okay, so I'll then end this section about group invariance for now with something about being heteroidal and irreducible. So this is Dodal, Karpovich, Leininger. And they proved that if your automorphism is heteroidal and irreducible, then all the periodic finitely generated subgroups of F have finite index. So in a way, being irreducible is a statement about invariant free factor systems. Being heteroidal is a statement about periodic cyclic subgroups. And this theorem is saying if you have those two conditions together, then actually all finitely generated subgroups that are free periodic, so that get sent back to themselves out to conjugacy, have finite index in a free group. And it goes the other, this is an if and only if. The other direction is obvious because, well, if all finitely generated subgroups have that are free periodic have infinite index, none of them are cyclic. I assumed my F had rank at least 2, so none of them are cyclic. That gives me heteroidal, and none of them are free factors. So that actually gives me fully irreducibility. So much stronger than just being irreducible. So that's what they prove, and this statement here is obviously invariant under passing to powers. So being heteroidal and irreducible is a dynamical invariant. But irreducibility, remember, is not dynamical invariant on its own. All right, so now a theorem that I proved. And I wanted to talk about coherence of these groups because it kind of came up, but I just ran out of time, so I'm not going to show you how I prove this. But essentially, if you have a periodic finitely generated subgroup, then you can pass to a power and assume it's fixed. And if you restrict the automorphism to that subgroup, then you can consider its mapping torus. And so having periodic finitely generated subgroups gives me free-by-cyclic subgroups in G phi. And I proved that's an if and only if. If you have a free-by-cyclic subgroups in G phi, then that corresponds to some phi periodic finitely generated subgroup. So I proved that this condition over here is equivalent to all free-by-cyclic subgroups of G phi have finite index. And this uses coherence that was proven by Fein and Handel. Very beautiful result, but I just don't have the time to discuss how it goes. And now here, this turns out this is a group invariant. This statement, I started with something that was dynamical. Now this is a group invariant. So that tells me being heteroidal and irreducible is a group invariant.
That's finitely generated free-by.
Oh, yes. That's part of my definition of free-by-cyclic. Let me put it that way. When I say free-by-cyclic, the free is finite rank. Apologies to some people in there. Okay, and then now let's talk about geometry. QI invariance. So QI invariance. We've talked about group invariance. Now QI invariance. Theorem of Makura from 2002. All right. And then there's a recent note by Mark Hagen that sort of uses I don't know, modern terminology or things that were introduced much later than Makura's paper, and that sort of modernizes the result in a way. Hagen a couple of years ago. And it states that if phi is polynomially growing, then your free-by-cyclic group has polynomial divergence. Unfortunately, I don't have the time to define what divergence is here, but you're sort of trying to see how quickly geodesics, quasi-geodesics move apart. And so this is sort of a natural QI invariant. That's the point that I want to make. It was introduced by Thurston essentially to kind of study like distinguish the mapping torus of the identity map on a surface from the mapping torus of a Dane twist up to quasi-isometry. And so I mentioned Hagen has a recent paper where he proves, he replaces talking about divergence with a notion of metric thickness. So G phi is thick. Again, this is a notion that's mainly trying to capture how much it feels to be relatively hyperbolic. Thick of order. Oh, I didn't say what the degree is here. Thick of order degree of your automorphism. And here it has polynomial divergence with degree 1 plus the degree of the automorphism. So that ends up telling you that the degree of the your polynomial growth is a QI invariant. Almost. There's a caveat. We don't know whether exponentially growing implies exponential divergence. So that's going to be the next theorem. So the following are equivalent. And Francois stated this. Your automorphism is exponentially growing. 2, G phi is relatively hyperbolic. And over here, I'll say non-trivially. So I'm not allowing being relatively hyperbolic to yourself relative to the whole group. And the third condition is G phi has exponential divergence. And so for the sake of time, I'm sorry, I'm not writing out all the people who've proven things here. Yes. Yeah, exactly. So so 1 implies 2 was claimed by Gotero-Lustig, but the proof was incomplete. And there were independent proofs by Damani Lee and Pritam Ghosh, proving 1 implies 2. And then 2 implies 3 seems to be folklore, but there's notes by Alessandro Sisto that sort of write this down, but I don't think it's published anywhere. And then 3 implies 1 is exactly this theorem of Makura, which is not one means polynomial growth, implies polynomial divergence, which is not exponential growth. So not one implies not three. So all those people's work together gives you this theorem that being polynomial, like whether or not you're polynomial or exponentially growing, that's a QI invariant. And when you're polynomially growing, the degree is also a QI invariant. And so I would suggest if you can prove this to just sort of finish this up, Papasoglu proved that having a cyclic splitting is a QI invariant. And in fact, in this setting, that minimal subgroup system is unique, is also sort of like a QI invariant. So if you could prove this, then you will give a new proof of this statement over here. That doesn't involve, maybe not a new proof of this statement, but a new proof that polynomial growth is a QI invariant. That doesn't go through relative hyperbolicity. And I think it's kind of like a neat idea that only came up to me as I was preparing these notes. Like, so prepare notes for your stuff, and it might help you make new connections.
You have any questions for David? So you can see a theoretical behind it.
Yeah, they have a normal second, but it's that.
What she said. Yeah, like you go far out, you can go up, and then you can connect things. It kind of looks like Z squared in a way.
That theorem that you have there, you're talking about it, does it use the idea of the proof for coherence? You just kind of go through the proof and proof that way, or?
Yeah, I'm exactly using not just coherence, but the exact presentation that they give in the coherence proof.
Okay.
So yeah.
It's a nice proof.
Very beautiful result by Finn and Handel, yeah. And also not just that they prove that it's finitely presented, but essentially the presentation is spherical. So I can even compute the Euler characteristic from that, and that actually plays a role in the argument.
Is the isomorphism problem decided for polynomially growing?
I don't know. I think Naomi Andrew will know best.
Okay.
I don't know. I've not really thought about polynomial growing things.
When G5 is relatively hyperbolic, what are the peripheral subgroups?
Well, you can have lots, right? But I guess in this proof here, they prove that you can have a relative hyperbolicity relative to the. So if you're exponentially growing, then there is a maximal polynomially growing subgroup in your free group, and it's invariant, so you can take its map like mapping torus, and those are going to be a peripheral subgroups in this implication one implies two. But once you have that, you can put lots of different relative hyperbolic structures.
And then is that one of the groups that comes up in the filtration?
No, so no, it's not a. It's not necessarily even a free, like it doesn't come from a free factor system. So maybe think of like if you have a once punctured surface, then the puncture can never appear as a filtration element because it's not a free factor. But then in here, it's going to give you like a Z-squared subgroup that's going to be a peripheral thing. So yeah, it doesn't. You don't necessarily see this in the filtration.
Okay. No more questions. We thank Cayley again.